when we're talking about multiplying polynomials, the first thing we need to know is how to multiply monomials, and that's what you're doing in question number 5. So talk me through why is it that 4x times negative 7x squared is equal to negative 28x to the power 3? What are you doing there? Say again? Okay, so first thing you're doing is you're multiplying the coefficients. So you're rearranging the 4 and the negative 7 to get them together. That becomes negative 28. So that explains the coefficient in the answer. What explains the x to the power 3? Yeah. So we had an x and we had an x squared. The x by itself is x to the power 1. And when you multiply two monomials, the exponents of the like powers add. X to the 1 plus 2 gives you 3. So multiplying monomials, you multiply the coefficients and add the exponents. Multiply the coefficients and add the exponents. Okay. So that was enough to get you through question 5, but as soon as we got into questions 6 and 7, now something else is happening. We no longer have monomials multiplied by one another, but now our polynomials can have multiple terms, and that's where we're going today. What we need before we leave this room at the end of class is a strategy for multiplying any polynomial by any other polynomial. And that's what we're ultimately shooting for. So when we multiplied in question 6, y to the power 3 times y squared minus 1, we were multiplying a monomial by a binomial, right? One term, y to the third, monomial, multiplied by a polynomial with two terms, y squared minus 1, that's a binomial. So what's the one thing that we need here that we didn't need before? What's the new part of your strategy? The process where we multiply both of the terms of the second factor by the first. What kind of a property is that? This is the one that starts with a D. It's a distributive property. So we need the distributive property here because while we have multiplication going on outside the parentheses, we have addition and subtraction going on inside the parentheses. So anytime we have a polynomial, something that has more than one term, it means that we have addition and subtraction happening inside of the expressions we're trying to multiply by one another. And so we're mixing operation. We're mixing multiplication with addition. And when those operations mix, their interaction is governed by the distributive property. So in other words, we just need to make sure that we multiply both the y squared and the minus 1 by the y to the power 3 that's out in the front. And so we end up with y to the third times y to the 2, and then added that to y to the third times negative 1. And when it comes to y to the third times y squared, how do you simplify that? Yeah. We're again multiplying monomials that have the same variable in their base. So the new exponent becomes 3 plus 2, or y to the 5th. So the final answer there is y to the 5th minus y to the power 3. And the very same property governs question 7, right? We're just distributing across 3 terms because our second factor here is trinomial instead of distributing across 2 terms. So the distributive property is kind of the star of the show in section 5.3, where we begin talking about multiplying binomials and polynomials more generally. So that's all well and good if we're just talking about numbers 6 and 7, because in both numbers 6 and 7, one of the factors we're multiplying by is a monomial. But as soon as we get to problem 8, now suddenly both of the things that we're multiplying, both of the polynomials that we're multiplying, have multiple terms in them. Number 8's an example of multiplying a binomial by another binomial. So what's different? What do we have to do in number 8 that's a little different than what we had to do in 6 and 7? What does that stand for? Right, so what we need to do is we need to distribute multiplication over addition. But because both of the factors here have addition going on inside of them, we end up doing a lot more distributing than we might have expected. What we end up needing to do is a technique that for binomial times binomial gets called FOIL. That's the acronym it usually goes by. What does FOIL stand for? Anyone have that off the top of their head? Yeah, Sierra.
First, outer, inner, and last.
The first, okay, and so that's the x times the 2x. The outer, what am I multiplying if I'm multiplying the outers? The outers are going to be x times 3 in this example. That's the first term of the first factor times the second term of the second factor. And then the inners, what are the inners here? The second term of the first factor and the first term of the second factor gives me the inners. And finally, the lasts, second term of the first factor times the second term of the second factor. So we end up with these 4 different products that we have to compute when you're multiplying a binomial by a binomial. 2 terms in the first factor, 2 terms in the second factor. So by the time we do all the multiplication, we end up with a total of 2 times 2, 4 terms, after the dust settles on our foiling. So let's step through these one at a time. What is the product of the first? So what is x times 2x? 2x squared. Great. The outers, what is x times 3? 3x. Not much we can do with that. So we'll just write that as 3x. The inners, 3 times 2x? 6x. So we'll get a 6x in there. And then the lasts, 3 times 3? 9. And so before we finish, before we do any simplifying, we end up with something that has a total of 4 terms in it, because we had a binomial of 2 terms multiplied by another binomial of 2 terms. Right? So we end up with 4 terms. What else do we need to do to this before we can be satisfied with the answer? And where are the like terms here? And when you combine them, they become 9x. Cool. So our final answer is 2x squared plus 9x plus 9. So FOIL and its cousins, its relations, are what's new. It's the last thing that's kind of new here. And it gives us this recipe for how to multiply one binomial by another. Keeping in mind that we always have to get 4 terms when you multiply something with 2 by something with 2. So that way you know if you accidentally skip a term, you'll be able to see that it's missing. So you can expect that there will be 4 up front. There are a couple of other ways also of keeping track of all of your terms when you're multiplying polynomials. Let me suggest a couple of alternative methods of bookkeeping. You can feel free to take them or leave them, whatever your comfort level is. But the reason I like these other ways is that they're they make it nicer when we start to ratchet things up. If I'm trying to multiply, let's say, a trinomial by a trinomial, I'm going to have a lot of terms running around to keep straight. So here are a couple of alternatives that you can feel free to discard or to use, whatever you're most comfortable doing. One of them looks like this. So if I'm multiplying x plus 3 times 2x plus 3. Another way of doing it is by sort of drawing out a little grid where the columns of my grid will be x plus 3. The rows of my grid will be 2x plus 3. And then each of the cells in this grid I'm going to fill in with the product of whatever is on its row and its column. So in the top left square, I'll fill in 2x times x, which was 2x squared, the product of the firsts from over here. The upper right, I'll fill in the 2x times 3. That turns out to be the 6x, which was our inners last time, 6x. I'll fill in the x times 3 in the lower left. That was our outer product last time, 3x. And then I'll fill in the lower right 3 times 3, the product of our lasts. And then I end up with all 4 of my terms. And because I kind of set up this grid in the beginning, I know exactly how many squares I need to fill in. It's one of the reasons I like this method. The other nice part about it is that now in the last step, I need to combine my like terms. And I can find my like terms, the 6x and the 3x, lying right there along this diagonal. So they're kind of easy to find, and I can add them together without having to hunt around to find them. They become 9x. And then I have my 9 from the bottom, and I have my 2x squared from the top left. we can use this method to multiply, say, 47 times 89. So I'll set up my multiplication. Let me actually put 89 over on this side, just so I don't clutter things up. And so then what you do, so 7 times 9 to get things started is 63. And so you'll write 63, one digit on each side of this little diagonal here in this little square, 7 times 9. 7 times 8, 56, goes in that square, again, separating the digits out. 4 times 9, 36, will go in the bottom. And then 4 times 8, 32, goes in this box in the upper left. And then the little diagonal lines come in, because now, to finish our multiplication problem, we can just add across each of the diagonal ramps. So our ones digit is just this 3 in it. Our tens digit ends up having 6 plus 6 plus 6, that's 18. So I'm actually going to carry a 1. My hundreds digit will be 1 plus 5 plus 2 plus 3, that's 11, so I have to carry a 1 again. And 1 plus 3 is 4. And so 47 times 89. So that method can be used to multiply multi-digit numbers as well, and it's often used, I think, when elementary schoolers learn how to multiply. This is one of the alternatives that they're now beginning to teach for how to do it. And I think the reason that they teach it is because it's an extensible algorithm. That same method that you use here to multiply numbers, you can also use to multiply polynomials later on, as we're doing today. Yeah. So because the lattice method works for multiplying numbers, we can also soup up the traditional multiplication algorithm to multiply polynomials as well. And again, if you like this, use it. If you don't like it, ignore it. But when we added and subtracted polynomials in the first section of this chapter, we used the so-called vertical method to do it, where we lined up the like terms above one another and just added down the columns. Well, we can use the same vertical method. The same vertical method can be used to multiply polynomials as well. So let's try it with x plus 3 and 2x plus 3. Again, lining them up one above the other, and trying to use the algorithm that we are familiar with for multiplying numbers to multiply these polynomials. So let's do the number problem real quickly over here. Let's say I'm multiplying 13 times 23. How do I do that using the digits? What happens first? In 13 times 23. 3 times 3. So you take the ones digits, multiply them together. That's going to give me 9. Then what happens after that? 3 times 1. So you multiply the tens digit by the ones digit. Multiply those together. That'll give me a 3. So now the 3, the ones digit of the second factor here, got multiplied by every one of the digits in the other factor. Then what?
The bottom row, start the 0 and then
Yeah, so when you move to the bottom row, you start by leaving a little blank space here. Some people put an X there, some people leave it blank, some people put a 0. But whatever you do, you need to bump yourself over a row. And once you've done that bumping, what happens? 2 times 3. So the tens digit of the second times the ones digit of the first. That's going to give me a 6. And then lastly, 2 times 1. The tens digits times the tens digit. So that'll give me this 2. And so now at that point, we've done all of the multiplying that there's fit to do in this problem. And once all the multiplying is done, what happens after that? The adding. Which, if we're still using the vertical method, we can do very easily because things are lined up in the columns the way we would want them to be. Right? What happens if we try using that algorithm with our polynomials instead of with our regular old numbers? X plus 3 times 2x plus 3. What do you want to multiply first? If we're following the same algorithm as before. Now let's take... So if we're following the multiplication algorithm from numbers, we would start with the ones digits. I mean, ultimately it won't matter because everything's commutative, but if we're following the algorithm, we'll start with 3 times 3 first, and then we'll move after 3 times 3 to the x times 3. So x on top times the 3 from the second row, and x times 3 is going to give you 3x. So far, that's what you end up with. Then, again, we're going to leave that blank space underneath the 9, the way that we did before. I kind of draw that in here, leave a blank space. And then what product happens next? Following the old system again. Yeah. I'm going to move this lattice out of the way so we get some space here. Right, so then the 2x times the 3 will happen. 2x times 3 is going to give me 6x. And finally, what's the last product? Last thing we need is the x times the 2x, which is 2x squared. So now that we've done all the multiplying, what happens to finish? Following the same algorithm. After the multiplying is done, all that's left is the adding. Same algorithm as when we multiply numbers. And in our vertical method, our like terms are already lined up against one another. So that when we add, we can add using the vertical method. And get, again, the same answer that we had before. So these are not really different in a sense. They're just different ways of organizing the information. And whichever way connects with you the best is the one I encourage you to use. If you like lattices and grids, use lattices and grids. They still work for polynomials the same way they did for whole numbers. If you like the vertical method, the traditional algorithm for multiplying numbers, the one we just did, use it. If you prefer the sort of the horizontal cleanliness of the traditional way to denote FOIL, then by all means use that as well. Each one kind of has its own set of advantages and disadvantages. So whatever your personal preference is the one I encourage you to go after.